Okay, hi everyone. I think we should start now. And hopefully there will be a recording of this webinar. So it would be available not just online, but also offline. But now we will consider solutions of different problems of the demonstration variants. Not because they are similar to those which you will see in during this year competition, but these tasks they are they will make sort of skeleton for the topics which could appear and to overall process. And also it could be used as part of your preparation, so you will know a bit better what you can expect from the competition's tasks. But still, just a kind warning that the problems of this year, they could be different. The topics could be different. There is no obligation on our side that the problems will be exactly of the same topics or of the same form. So if there is no questions, let's start, because we have many problems to consider. And I'm sure that not all of them will be discussed, but still we have some time. So let's start with 10th grade from the very beginning. So first of all, just to notice that the first 6 problems, they cost the same amount of points, 6 points each. And what you need to do is just to put a correct answer to the form. So let's consider the very first problem. So we call some sort of rectangulars nice, and we need to compute the total area of different nice rectangles. So it will be like the condition is that the lengths are integers, this a and b, and perimeter numerically equals to the area. So it's like twice a plus b equals a times b. What does it mean? Actually, it means that if we take difference of these things, it will be equal to 0, but the difference is very similar to some wiggling of the parentheses, like we should just add one additional term in order to get some nice value which is decomposable. So we get this sort of equation, not equation, but equality. And we know that both parts are integers and also A and B okay, and also we knew that A and B were positive integers before subtracting these doubles. So we have several solutions. First solution would be like this. Basically, we can come up with this sort of condition because this equation is symmetric under interchanges of A and B, and that means that if we just interchange them, we will get the same rectangular but with different order of sides. Like I would say, if A is less than B, then this one should be this side should be the short one, but in the different order it would be the long one. But basically that's the only difference. So we will have this sort of solution. We also should write like this. Another solution would be equal to 2. And there could be another solution when the opposite order, but it gives same set of A and B. And also the product could be positive using negative values, multipliers, and that means that basically we will have solutions with the opposite signs here, but we can definitely see that this one with -2, for example, it doesn't fit us because A should be equal to 0. But if we take -1, it could be something. Okay, and now let's check. So in this case, we have solutions A equal to 3, B equal to 6, and it gives us 9 in the parentheses, and totally 18, and the product is also 18. Here we have A equal to 4, B equal to 4, which gives us 8 here, and 16 as the left part, and 16 as the right part. And here it gives us A equals 3, B equals, oh, not 3, 1. A equals to 1, B equals to 1, but it doesn't fit this equality. It would be 4 equals, should be equal to 1, which is nonsense. So it also doesn't fit us. So we have these two solutions, these two different cases, but we should compute, like the task is to compute the total area. And you shouldn't confuse what they are asked to do. And total area here would be 18 plus 16 equals 34. And 34 is exactly the number which should appear as your answer in this problem. So your answer should be solo this number and nothing additional. No explanations in written form. Like the first 6 problems is just test part. Okay, good question. Like, can anybody hear me? Does the sound work? Because the system shows for me that the sound should work. Так, okay. Well, so moving forward, I will skip some problems because they are not of big interest. You just solve them. If you do that correctly, then you get the answer. So let's compute problem number 3 for the 10th grade. So we need to compute the integer part of some value, and the value is like this. So 1 plus square root of 5 over square root of 2 to the power of 6 plus something very similar but with minus sign. So first notice is that what we can see here are called conjugate numbers. What does it mean? In here, it means that the product of the conjugate numbers, like the numbers in nominators, like it is integer, and their sum is also integer, but still the numbers itself are not integer, and also they're irrational. Okay, what to do, how to deal with these conjugate numbers? Basically, we should group them, and we should use some regularities which we can find with them. So how to do that? So first of all, let's take this 1 over square root of 2 outside of the parentheses. It's a common multiplier. And the rest, we can write through binomial decomposition. So it would be 1 plus square root of 5 to the 6 plus 1 minus square root of 5 to the 6. And this part, it equals to 1 plus, and here we need these choose numbers, say 6 choose 1 times square root of 5. If you don't remember what are choose numbers, please refresh that. I will write it down here. Okay, so just refresh these areas if you need. But later on, we get something very nice of this. Second degree and plus the third term here, 6 choose 3 times square root to the power of 3, and so on, until we get to the 6th degree here. But it's just a part. So we will have another sum, the second part, will be plus. The term will be just the same, but there will be just one tiny detail which will make the computations much easier. Hopefully you already noticed the detail. So the thing is that we'll have slightly different signs here, and the signs will be distributed like this. Like for odd degrees, the first degree, the third degree, and so on, the signs before corresponding terms would be negative, and for the even degrees, like even degrees terms of the sum, the sign would be plus. That means that these terms with odd degree, it will just cross out, could be crossed out from the sum, and the terms they will eliminate. But what we get finally is the rest here is just this sum, which is doubled. So it equals to double sum of 1 plus second term. It will be 6 times 5 divided by factorial of 2 times 5 to the 1 plus fourth degree. It would be also the same factorial times 5 squared and plus 5 to the third. And the thing is that we almost eliminated all the not integer parts, right? Like the only non-integer term now is this term, which is basically 1/8. So we just compute the exact value. And what we get there is just answer 144. So if we do the proper calculations, it will be 1, 4, and 4. Okay. Any questions? Okay. No questions so far. Then let's move forward. So again, what you need to do in that problem, in the second problem, is just to give the correct answer. You wouldn't have, especially with the online tour, you wouldn't have any space to put solutions of this problem. So you will need just to give the correct answer. Next one. For example, system. Now, problem number 5. So we have this system. And the condition is 3x squared. I will write the degree a bit later. So 3x squared minus just 3x squared minus 8 8xy 8xy and minus y squared equals to 18. And here x squared plus y squared minus double x plus 8 times y plus 16 equals to 0. And what we need here to give the maximum value of x pi among the solutions of the system. And what we really need now is to make the condition correct. So it's squared, it's also squared. Squared here as well. And here. Okay. What can we do here? Actually, we can, like, that is the problem which, with a trick which happens in many different problems, when you shouldn't act straightforward. You should consider first some strategy of what you can do now and where to go with the next several next steps. So here, for example, it's not that clear what to do with the first equation, but the second equation, it looks more like you can make sort of decomposition. So you can write down that it is something related to squares of such numbers. And if you do so, you realize that you should be accurate with the free terms, like with the constant here, because all the rest of terms we already put into this parenthesis. So x squared minus double x, it would be indefinite part of this term, and we just miss one unit here, and we can add and subtract it. And also the same situation here. So we have y squared and 8y, which there is some minor mistake here. So if we should put plus here, of course, then we see that y squared and 8y, they sum up together to almost entire term of here, over here. But what we need also is constant term 16, which luckily is here also in this value. So what we need now is just subtract one unit from the left part of the equality, or just to add it simultaneously to the right part as we added it to the left. I will choose the second option, and finally we get this equation of this form for x and y being integers. What does it mean? It means that we have squares of two integer numbers, and sum of these squares is equal to 1. But each of them would be like minimal, minimal possible value for each of them is 0, and the second least value is 1. Any other case will give us more, which means that we have just these two options for these values, and also that means that as it's a square number, so that means that if this value equals to 0 or 1, then module of the value, the absolute value, would be also equal to the same, to the 0 or 1. So we can rewrite this to very nice condition that either x minus 1 equals to 1. And module y plus 4 equals to 0. And it is sort of system. Or the second option is that module x minus 1 equals to 0 and module y plus 4 equals to 1. And basically that's all possible what can happen here. And we can easily write down the 4 solutions of the second equation. I recall that it is just solving the second equation at the moment, and already so many information. So the first solution, x1 equals to say 2, and y1 equals to minus 4. Fast in text as text. So x2 equals to to 0 and y2 equals to minus 4. I wouldn't use this subscript here. I will just write x2 and so on. x3 equals to 1 and y3 equals to minus 3 and x4 equals to 1 and y4 equals to minus 5. So that are all the possibilities. But again, it's just solution of the second equation. So what we need now is just to pick up those who fit us well and recall the task. The task is find the maximal value for xy among the integer solution. So as you can see, checking, like verifying the value using the first equation could need some computations, which sometimes cause some unexpected, unwilling mistakes. So maybe we can choose some easier way how to understand, and definitely there is an easier way. For example, we can consider the product itself. So what we can do here very easily is just to consider the product to fasten and to make faster. You can consider the E So to make the computations faster, we can consider the easy way of what could be computed. And here, the easy part for computations is computing the product. So the product here would be -8, here would be 0, here would be -3, and here would be -5. And definitely 0 is the maximum among all these guys. But does it fit to the equation? If we put this solution to the equation, it would be 0 minus 0 and -16. -16 doesn't equal to 18. So this guy over here, it just doesn't fit. And if we now consider the next case with x equal to 1 and y equal to -3, then you can easily compute that it fits to the equation. That means that even if some other solutions also are valid for the first equation as well, then that just doesn't mean anything for us. The answer would be -3 because it's the maximal product among all the solutions of the system. Next problem. So let's move to the hard ones. Consider let's consider problem 8. So a circle is inscribed in an isosceles trapezoid. With bases A, B, and C, D, and the circle touches the sides at some points. At points, like it's important for us that BC is touched at point T. And we need to compute AB over CD if AB over AD is equal to a given value. So it is geometry, and that means that it's already another block of problems, the second block, and that means that for this problem you should give brief solution, like thesis solution, and I'll try to illustrate not just solution of the problem but also how it should be written down. So what we have here is the circle, and the trapezoid. Oops. it should be isoscales, and the circle should be inscribed. Something like this. And here we have these points. A, B, A, B, C, D, and also what is of interest of us is this point T, and also another interesting point is point F. So if we take AT and extend DC, we get this point F over here. And what we need is to compute AB over BC or over DC. What's that? How much is that? Okay, what to do here? Like, first of all, we need to use somehow this condition, AP over AT. And I didn't write down one more point here. So another point is here. It's point B. So what we need is to use this condition AP over AT equals to 7 to 23. Okay. But we can use it in a natural way. We can write down that let AP equals to AP equals to 7A and AT equals to 23A for some real number A, real positive number. And also what we can use here is sort of special property of a section line to a circle and a tangent to a circle. We can write down the famous equality that AP times AT equals to, and here we need the point on the bottom, so the point would be called M. So we can write that AP times AT equals to AM squared. So we can give names for these parts as well. Let it be X, and also the parts of side DC let be Y and Y. And I write equal parts because it's isoscales trapezoid, and it's inscribed circle. That means that the picture is symmetric, respectively to this vertical diameter. Like radius, which comes from the center of the circle to M, it would be perpendicular to AB, and also it will be perpendicular to DC, exactly like radius coming to Y. Like that pretty obviously shows that this line would be diameter, and it will be perpendicular to both bases of the trapezoid. Okay. From here, what we can get from here? Actually, what we can get from here is very nice thing about the points on top. First, we can rewrite this equation in the following form. So, in terms of A and X, we can write down that this equality means that 7 times 23 7 times 23 A squared equals to AM squared, which is X squared. Okay, and this is the first equality. What we can get next? Actually, we can use the property of tangents to a circle and write down that this segment here is X, and this segment here is Y. And also what we can do is to draw this line, which is median of the triangle ATB, which divides the base of the triangle AB at the middle point M. But we can see that the triangles here, they are similar. The triangle ATB and FTC, they are not just similar, they are homotetical, which means that all corresponding parts, they are similar. And from this, we can easily get that the median, the prolongation of median TM will become a median TK. So we can denote this point somehow, big point K. And we can write down this property. So triangle ATP is similar to triangle FTC. That means that TK is also a median. Like, it's not the entire proof why it's median, but it's the conclusion, and the proof could be made easily in different ways. Those who know homotopy well, they could do homotopy to fit the triangles to each other. Others could use similarity of the triangles and the corresponding parts of the triangles, and use the similarity coefficient should be the same for segments CK and MB, like between this pair of segments and pair of segments FK and AM. So there are many ways how to do that, but the outcome is the same in all of them. So that's how we know that these two segments will be equal. But from this lower triangle, we know that segment TB equals to segment MB, and so the same we should be able to say about the triangle TCF. So TC equals to CK. And we can write that, we can draw that. So all these segments are equal to pi, and these segments are equal to x. That's why we denote it slightly differently. Okay. And now what we can do is just to write down another property. So initially, like in here, we use the property of point A. We use this property over here. But now we can use it for point F as well. So the product of section of parts of a section line passing through F and crossing, secting this circle and in points D and P, it would be equal to square of tangent segment. Which gives us the condition that FC squared equals to FT times FP. And now we almost get this computational part, which we can use for computing something. FC, it equals to this thing here. It equals to, oh, sorry, not FC. This point should be N. So it was a mistake, sorry. So square of a tangent segment, which is Fn, right, from the point to the tangent point, Fn squared. This is sort of like, I will write down this square a bit later. Fn, or we can write down times. No, I will write it. I will write the square later. So Fn squared equals to Ft times Fe. And not forgetting about the square. So the square of tangent segment is equal to product of segments on the section line FT and FP, all coming from the same point. And thus we have that Fn is just triple y. Triple y squared equals to, what we don't know here is definitely segment FT, but we can try to do something with that. That's why we call this FT. And we add the rest to FT. And the rest is TP, which is part of AT segment minus AP segment. So that is basically just 16A. And now what we have here, is just some relation between Y, FT, and A. But also we can write down that TF divided by TA is equal just ratio of Y and X. So we can write down that also we have this TF over AT equals to Y over X. And this equation, it gives us some sort of relation between TF, which is again this undefined, unknown segment, AT, which is basically something measured in A segments, it's 23A, and Y and X. So we sort of know something about TF over Y, because we can rewrite this as TF over Y equals to AT over X, and AT is 23A. So let's just divide all this stuff by y squared, and we will get the following thing. We will get 9 equals to oh no, we will divide not by y but by ft squared. We will get y over ft squared here, and it equals to, like, one ft just eliminates from the left part from the right part, and another one appears to 1 plus 16a over ft. And this guy, it's 16, and we almost done with with this, because now we can write down what is y over ft. So it's y over ft, it's x over at, so it's 9 x over at both squared, but now we can substitute these guys. X squared is 7 times 23a squared, and at squared is just 23a squared. So we can write down this stuff pretty easily. So it's 9 times 7 times 23a squared over at squared is 23 times 23 times a squared, and this guy, it equals to 1 plus 16 ft. But already now you can notice that some terms will eliminate here. So we know this ratio now, so we know the left part of the equation. It's 63 over 23, and from here we get that ft don't forget this. So from here we get that ft with 16a over ft 16a over ft it equals to some numerical fraction, which is pretty nice. It's 40 over 23. Which finally gives us that the result here for the entire problem would be like AB over CD under a similarity of triangles. It would be equal to AT over TF, which is computed, and it equals to 2.5 or 5 over 2. And this is the end of the solution. Okay, and you saw the process of solving, and basically, like we came up to a bit more things which is written down here. So normally you will give a bit more explanation in a regular solution, but here you just go through the main parts. So I would say that in here it would be important to write down first this. Second thing to mention would be this. This and this. This would be third. This could be written down as fourth. Definitely, like normally you need to write down this about these segments, but here, like, you can mention that, but it's not the main part. And the last part is like the final computation. No, better I would write down like fourth part. Fourth step would be about the segments. And fifth step would be about the equation. And after that, immediately I would write down the answer for the problem. So what you need here is just partial solution, like not partial solution, but you need entire proof, but you needn't write it down entirely. So you need just this thesis solution, like each paragraph of your solution should be packed into one phrase, like one phrase, one equation, and instead of the entire solution text, you write down just these titles of the paragraphs, the main ideas. Okay, and like as I mentioned earlier, it's not the main point to look through all the solutions. That's why we consider just one more solution at the moment, the solution of 11th grade last problem, which is which is considered to be the hardest problem. Like the last problem of 10th grade was also hard, but like two of them, they are of comparable hardness. So in these two problems, like the problems 9 and 10, the numbers 9 and 10 are the hardest problems of a task, and for these problems you need to give the entire solution in written form, just as on regular national Olympiads, or like on the main international Olympiad, International Mathematical Olympiad. So just entire proof, the whole text should be written down here. So what to do with the problem 10? So we are switching to the presentation mode. Okay. So the problem was about points on a plane which are colored two different colors, and some of the points are connected with others with segments. So who knows, that means that we have some graph here. Consider a graph. And each minute simultaneously all points which are connected with even number of points of the same color, sorry, it's like typo here, which are connected with even number of points of the same color, are colored the opposite. Are colored the opposite. So basically we have several points Some of them are connected with segments, and the points are colored two different colors, say red and green. And the picture, it changes each minute. It changes according on the colors on the previous minute. So what we need this green vertices, and we need red vertices. We understand that the total amount of this is 2021. And sorry, seems like I cannot write to this angle normally. I'll try it once more. Okay, 2021. But what also we know that there are those numbers, vertices among like each minute among vertices which are green. There are those which have odd number of green neighbors, and there are those which have even number. And here also those who have odd number of red neighbors, and here even number of red neighbors. The question is, what are the quantity for this one? So basically it's subgraph with green vertices some of them connected with segments in such a manner that each degree of each of these vertices, like which are in this subset, being odd. But also there is a theorem about the quantity of vertices of odd degree in a graph with all degrees being odd, there is an even number of vertices. Famous theorem from graph theory, and like you can check it, prove it by yourself if you don't know. So what does it mean? That means that taking these vertices which are green and which have odd degree, which is basically the same as odd number of green neighbors, then this quantity it is itself, it's even. And absolutely similarly, have that for this subset of red vertices which have odd number of red neighbors, that is odd degree, they are also even, they have even quantity. So that means that like green number of green vertices, it's sum of quantities of vertices in these two subsets, like those who have odd degree plus those who have even degree. The same for red vertices, and the total is 2021, which is odd. So that means that as this subset and this subset, they are even, that means that sum of these two guys is odd. Sum is odd. But that means that on each step of the process, the number of vertices which change their color is odd. But the same we can say about any step. That means that just for each odd number of steps, the change would be in odd number of vertices, which is not zero. So the totally same picture couldn't appear in odd number of steps, which finishes the proof. So that's it, we done it. That's basically that's everything for today. So we will do a presentation with the solutions, which you can download and like watch yourself, and not just these problems would have solutions there. So that's not a big problem that we saw just several solutions of the entire list. Now you can see the process of solution from the very beginning till the very end for some given problems. So we considered problems from all of the three parts, and we saw the difference in the form, what we should write as an answer. So in the problems 9 and 10, we should write down the entire solution. In the problems 7 and 8, we write just thesis solution, the titles of paragraphs, I would say, and the final answer, numerical answer. And in the first 6 problems, we write down just the answer itself, no comments, nothing additional, just answer solo. That's more or less everything for today. If you have any questions, we still have like maybe a couple of minutes to answer the questions. But if no questions, then we finish for today. Okay, I cannot see any questions, so thank you for thank you guys who attended the class online. Thank you guys who will watch it offline. I wish you the very best luck in the competition. Please train and do your best on the competition, and hopefully we will meet either for getting prizes or in Moscow when you study here. So I wish you very best. Goodbye.